couple of key takeaways from here. Number one হচ্ছে that if you cut magnetic field lines at a constant rate, EMF induced হয় না. Also, the thing is that this formula is what you need to apply, which is minus n d phi by dt. You need to have a change in magnetic flux for EMF to be induced. And this is something you learn in your O-levels. It's called the Faraday's law of electromagnetic induction. Okay, so Faraday's law of electromagnetic induction states that the rate of cutting off magnetic field lines results in EMF induction. And আমাদের A-levels যেটা focus করতে হবে, I'll show you the bigger picture. So A-levels যেটা focus করতে হবে is to convert your phi graphs to EMF graphs. So তোমাদের কি EMF এর value গুলো বের করতে হবে. So a very common type of question is this one. They'll say that the magnetic flux changes in this way. How does the EMF look like? So you need to be good at differentiating visually. মানে যেটাকে differentiate করলে এটা আসবে না. So what's the differentiation of a flat line? What's the differentiation of a straight line passing through the origin? So that's basically what it is. Okay, so that's what we did last class. আজকে হচ্ছে we'll be doing something that's new to your not new actually. মানে A-levels এ focus বেশি. It's called the Lenz's law. So এটা করব আমরা. So do you have any questions from this? এখান থেকে কি question আসতে পারে একটু just বলে রাখি. They'll give you graphs and they'll ask you to find the EMF. What are you supposed to find from that graph? The gradient. Okay, slope we বের করতে হবে. I think review there are a couple of questions of similar type. এই যেমন এখানে হচ্ছে কারেন্ট দেওয়া, কারেন্ট থেকে phi তে যেতে হবে, phi থেকে EMF এ যেতে হবে. This whole thing is like a graph thing. Now this is easy because this is a sine graph থেকে differentiate করে কি আসবে is usually much easily understood. What's the differentiation of sine? Cos, right? So eventually you can একটা cosine graph মতো আসবে. We'll come to that later on. But the point I'm trying to make is that তোমাদের graph analysis করতে হয়. Yeah, this is the one. So do you see this random shape here? They want you to find out how does the EMF look like for that random shape there. কত দিচ্ছে 3 marks. Okay, I have seen up to 5 marks same question. Okay, so এরকম question anticipate করো. Main idea here is to be able to understand how a differentiation works graphically. Is it like this? Okay, so ওই জিনিসটা. Anyways, yeah, পরীক্ষা ছিল. This one. আচ্ছা হ্যাঁ, এটা তো আমরা ক্লাসই করছি, এটা সবাই করতে পারবে. All right, so let's see if you can recall what we did last class. So this is a question. তোমার এখানে হচ্ছে উপরে কারেন্টের গ্রাফ দেওয়া. Now you might be wondering, কারেন্ট থেকে তো EMF করি না আমরা, কারেন্ট থেকে আমরা phi থেকে EMF করছি. It's not a big problem. It's the way current changes. It's exactly the same way what changes. Phi. Because current comes from the phi comes from the current, right? So আমার যদি current এভাবে fluctuate করে, the magnetic flux will also fluctuate in what way? Exactly same way. So we can rather write in current here, we can consider this to be a what graph? Phi graph. Achha, phi and current are directly proportional. It's a free mark they try to give you. যে কোন current graph দিল আর বলো phi draw করো. It's exactly same. Nothing can change here. Okay, because magnetic flux is generated by what? Current. The way current changes is the way magnetic flux changes. However, EMF is not from magnetic flux. It's the rate of change of magnetic flux that produces EMF. So yeah, আমাকে একটু বলতে পারবা কি করতে হবে? I'll walk you through the process. A flat line এর differentiation কি হবে? Yep, so it's a flat line here, like that. It's a curve like this, right? এটা differentiationটা কিরকম হবে? এটা একটু tricky. Now কি করব বলতে পারো আমাকে? It's like constant up, constant. Yes, that's what we do. So আমরা যেটা করব এখানে firstly we're going to draw a tangent. And is it a steep tangent or a flat tangent? Steep. And is the steepness of the tangent becoming greater or lower? Lower, right? And কমতে কমতে এই জায়গায় কি হয়ে যাচ্ছে? Flat. So that means the gradient is highest at the start. So you actually start with a high value. Okay, randomly just high value, and that value starts decreasing until it becomes what at that location? 0, right? So the graph is supposed to look something like this. এই যে 0 হয়ে যাবে, okay? And then you have again a flat line. What does that mean? No gradient, okay? Because it's a flat line, right? So again 0 there. And then এই পার্টটা তো অনেকের প্রবলেম হয়. This graph goes down like that. So is it a constant gradient or a variable gradient? Constant gradient. Is it a constant positive gradient or a negative gradient? Negative gradient, right? So how would this graph look like? নিচে একটা flat line. Okay, that's it. Now, এটা যদি অনেক আগের question paper হয়ে থাকে, এটা কোন year না? So I don't have the year here. If it's a very old question paper, it is an old question paper. Some of the questions of pre-2015 there. So if it's an old question paper, sometimes they want the answer to be a little different. Can you tell me technically what has to be a little different here? Flip করতে হবে, okay? Because you know the minus EMF data হয়. So modern, like recent papers, they don't care about it. I think I told you last class why. Because you know the voltage value is subjective, how you connect your voltmeter, right? But this is how it should be, right? So that is it. Did you get this? Why?
We thought I equals E.
Oh, you thought I equals to E?
Yes, D equals I am.
I don't think even an O-level student thinks that way. For 3 marks, just say graph and drop with them. So. No, how does that make a difference? Question to any to answer করতে পারো না. Here like key difference হবে. আচ্ছা। এটা এমনি question search করলে তো marks কিন্তু চলে আসে. It is very easy. The indexing of question papers is very good because people keep searching just দুইটা word লাগবে দেখো এটা পড়ে আসবে. It is like that. So you haven't searched enough. Okay, so I mean ধরা খেয়ে গেছে যে তোমরা search করছো পাও নাই. Anyways, we'll start our next topic. Gradient. Oh, acha, হ্যাঁ, এখানে ওই ইস্যুটা নাই, but again, if your graph had something like this and then something like that, obviously this would be a lower value, this would be a higher value, right? So you know it'll be something like this, and then that'll be something like that. Okay, so that's how it's supposed to be. Okay, let's move on. আজকে আমাদের অনেক কিছু করতে হবে, Lenz's law especially. So we have seen Faraday's law so far. Faraday's law of electromagnetic induction states that the EMF induced is directly proportional to the rate of change of magnetic flux. According to Faraday's law, if you cut magnetic field lines, what will be induced? EMF, right? So let me show you with an example here. Last class, maybe I shown this, but about that. Okay. So yeah, you have a magnet here, and if I take the magnet and I move the magnet here, like let's say this and that, you can see that as I move the magnet in and out, right, it produces an EMF and a current because it's a complete circuit, right? But if I move very slowly, I get a very low output. If I move very fast, it's a very high output, right? So this is something you learn in O-levels. In fact, O-levels a chapter tomorrow details there was a device we had in O-levels called as generator, where it rotates and cuts magnetic field lines and everything, right? We have that in the AC chapter. AC currents but this is something you have seen. But it's a little different. It's not the working of a generator. It's not the working of Faraday's law, because we assume that you know that. This very strange phenomena that takes place. What is this strange phenomena? So the phenomena is that you have this coil here, and a 4 marks student question to demonstrate Lenz's law. So you take a coil and you connect this coil to this device called a center zero galvanometer. It looks like this. Okay, this is called a center zero galvanometer. What is it? So galvanometer is a device that allows you to see the direction of current flow. So current কোন দিকে flow করে এটা দেখায়. Okay, it's very sensitive, but it can pick up very small changes. So this is called a center zero galvanometer. It doesn't give you magnitude. Keep that in mind. No magnitude then. It only gives you the direction. Okay, and you have a coil at the top. And what you do here is you introduce a magnet. Okay, so this is a magnet here, and bar magnet, typical bar magnet, and you bring it close to this coil. Right, so bar magnet, and you can place it inside like that. Now this magnet has poles here, so you have your north pole and the south pole there. And what's around the magnet? magnetic field lines, right? Can you tell me how the magnetic field lines look like in this case? কিরকম দেখতে? What's the shape of the magnetic field line around the bar magnet? Yeah, so it's just something like this, like that, like that, like that, like that, and it goes this way, that way. Do you agree? এরকম দেখতে? Okay, fine. So that's how the magnetic field lines look like around this magnet. What we're going to do right now is take this magnetic নিয়ে আমরা যেটা করব is we will place the magnet inside the coil. So tell me what happens, okay? Right now the magnet is right next to the coil. Can you tell me what's the deflection? The magnet is not moving. Okay, so কি হবে? What's the deflection going to be? Nothing. Why? Because there's no change in magnetic field. Keep in mind, a strong magnetic field doesn't mean EMF. What needs to be there? A change. Even a very weak magnetic field can produce EMF as long as what is it doing? Changing. Okay, but so the idea is that the strong magnet is not our important requirement. Our requirement is a change in magnetic field. So কিছু হবে না এখানে. You move it right now. You keep it here. Nothing happens. You start to move it slowly into the magnet, right? You'll start to notice what happens. The thing starts to move like that slightly and comes back again the moment you stop. But let's see what happens next. If you move it in at a very high rate like that, let's say you go all the way in like that, you'll find that there's a very large deflection, maybe this way or maybe that way. It's subjective, it doesn't really matter, but so when did that happen? You took the you took the magnet and you put it all the way in like that, right? You moved it like that. So that's why it produces this deflection. Now, what we're going to do is we'll repeat this thing. আমাদের এই same জিনিসটা আবার করব এখানে, but this time I'll keep the magnet in like that. Can you tell me what would the pointer do? It'll come back to rest. Do you agree? Acha. And then if I move it the other way around, you don't need to be A-level knowledge লাগে এটা বোঝার জন্য. If I go the other way, again there'll be a deflection. Which way should the deflection be? The opposite way, right? So when you bring it in, I'll show you the bigger picture here. When you bring it in, there is a deflection. And when you're stationary, there's no deflection. And when you bring this out, there's a deflection. Do you agree so far? Okay, we'll take this one step further. It into O-level standard basic. This is basically the evidence of Faraday's law of electronic induction, that when magnetic field lines have been cut, what is it produced? EMF. But we'll take it one step further. Further, as you bring this in, right? As you bring this in, magnetic field lines are being cut, EMF is induced, and because of that, something will be generated in this coil. Listen carefully, okay? You take this magnet and you bring the magnet in here. The magnetic field lines are cut, EMF is induced, and this is a complete circuit. So because there's EMF in the coil, what will start to flow? Current. So you'll see current is flowing through the circuit. That's what this, does its thing. But then somebody became curious that, wait, there's a current in a coil. That is something we've seen before. কোথায়? Current in a coil. এরকম একটা coil আছে এখানে, and there's current in this coil. Any direction, right? What happens then? Huh? Yes. So whenever, by the way, this is, I think 5 classes back, okay? It's not something new. So when you have current passing through a coil, right, you'll find that there is a magnetic field generated around the coil that looks like what? The magnetic field of a magnet. This is the idea of a solenoid, right? So you can get a notice for if current passes through this coil, right? And this is the front part of the coil. Can you tell me which side will be the North Pole? Left side, right? You use the right-hand rule. Right-hand rule, there are your fingers on the front for the current. Your thumb represents the what? North Pole, right? So you'll find on this left-hand side, there is a very strong, or just a North Pole generated here. So this side is going to be a North Pole. And on the other side, you'll find that you have a South Pole. Do you agree? So whenever there's current in a coil, right? And if you don't believe that we have done this, I'll just show it to you. Whenever you have current in a coil, right? You remember the flat circular coil? Amplify core, we make this thing. What is this thing called? The solenoid, right? So whenever there's current in a solenoid, what is produced around the solenoid? A magnetic field. A magnetic field that mimics what? A magnet, right? That's why we call this a what magnet? An electromagnet. Question হচ্ছে, the person who was doing the experiment wondered, যে কারেন্টটা ফ্লো করতেছে আমার কয়েলের ভিতর দিয়ে, এই যে here, এই যে এই সার্কিটের ভিতর দিয়ে একটা কারেন্ট ফ্লো করতেছে, he wondered what kind of magnetic field would that produce, like kothai north, kothai south. And that's when something interesting showed up. He found that whenever you bring the north pole into the magnet, right, there's EMF induction, there's a current generated, and that produces what around this coil on its own, a magnetic field. And that magnetic field happens to be such that it actually opposes your magnet. মানে হচ্ছে এই সাইডে we end up getting a what pole? A north pole, right? And ওই সাইডে হচ্ছে south pole. This is a little strange. Why? Because it's like the system is resisting the change, right? Then obviously, as you take it out, deflection যেহেতু উল্টা দিকে, currentটা উল্টা দিকে, which would mean that on this side, now you have a what pole? North pole. And on the other side, what do you have? South pole, which, by the way, opposes the motion again. Okay, so what was observed was that whenever you bring a magnet in, magnetic field lines have been cut, EMF is induced, a current is generated, it produces a magnetic field to oppose this motion. It's like self-opposing the change. It's quite ironic because whatever the change is was induced by the movement itself. So it's a chain reaction to boliki, when the sequence of event, you move this, which induced what here? EMF, which generated what here? Current, which generated what here? North and south and magnetic poles. And that pole that you created is what? Opposing you, right? This idea is called the Lenz's law. So Lenz's law came along and explained the fact that whenever you try to distort a magnetic field, right, the system will try to what? Prevent that. Why? Why is it like that? Not that they'll ask you, but key with the very reason. Huh? Newton's third law. Questionটা হচ্ছে oppose কেন করে? Nature wants to be in equilibrium. Acha, that's actually the philosophy of everything, but that's not the answer they'll accept, okay? Because you can actually write that for everything and it'll be true, but they won't accept this. So the reason is actually based on energy. I'm বলি কি হচ্ছে, as you move in, listen carefully, okay? It's an energy version. I have not seen them ask yet, but I think you should know this, okay? So as you bring the magnet in, what kind of energy do you have? Kinetic energy. That K is used, it's used by the coil to cut the field lines and generate what? Current. So the K is used up by the current, right? Which means that the current is increasing, the electrical energy is increasing, which would mean the K must be what? Doesn't that mean the magnet should slow down? Right? That slowing down is done by this system. Because the system is taking energy, it's eating up the K of the system. It's the energy version of the answer, like energy conservation again. It's very similar to what you've seen with charges. Remember a positive charge, positive charge. If you bring the positive charge towards the positive charge, what does this positive charge do? Lose energy because it's doing work against it, right? The system does work against it, K is lost, and as a consequence, what is increasing here? Electrical energy. That's the reasoning from there. Because think of the other way. Jeta slow down করতেছে না. It means infinite energy. Why? তুমি K দিয়ে যাচ্ছ, electricity generate হয়ে যাচ্ছে. What's the transfer? Because এটা তো loss হচ্ছে না. তাহলে এটা কেমনে gain হচ্ছে? So to balance that, as he mentioned, the nature wants to be in equilibrium. It can only do that by stopping the system and using the energy to create what here? Electrical energy. And that's the fundamental reason behind it. Tomorrow's syllabus, you don't need to know it. You need to just recall Lenz's law exists. In what context? That whenever you try to do something, the system tries to what? Oppose it. So as you try to bring it in, it'll try to push you out. As you try to go out like that, it'll try to what? Bring you back in. It always tries to oppose whatever motion is going on, right? And this is called Lenz's law. And you get the most randomest questions in your syllabus. Their focus of it. I'll show you examples. Just random things there, okay? Very interesting things, by the way. But yeah, this is your Lenz's law. So what's the definition of Lenz's law? Lenz's law states that the EMF induced generates a current which produces a magnetic field such that it opposes the motion created in it. Okay, so the original motion that you create for it, and like the oppose for it. Clear about that? Right, so that's the Lenz's law. Now, where else have we Lenz's law, like we have to use Lenz's law? So there's one small part here that last class is actually jeto, but এখন দেখাই তোমাদেরকে. Remember we cut the magnetic field here. This magnetic field, we cut the magnetic field. So if you cut the magnetic field, what is induced here in this coil? EMF. And if it's a complete circuit, what will be generated there? Current, right? A current কোন দিকে flow করে ওইটা আমরা একটু বের করার চেষ্টা করব। Okay, so let's try to see which way it flows. So তোমরা একটু figure out করবে এটা। Can you tell me before we get into cutting of magnetic field lines, আমার যদি এটা পজিটিভ হয় আর এটা নেগেটিভ হয় আর এটা যদি নর্থ হয় আর নিচেটা যদি সাউথ হয়, can you tell me which way force will be generated? কোন দিকে force exert করা হবে? Right, which way is the force? Okay, এদিকে দেখি FBI. Current is from here to here, magnetic flux is downwards. Will it go this way or that way? Yeah, so that's the direction, right? So basically what you'll notice is that as you apply current here, a force would be generated that way. What do we call this effect? Yeah, it's called the motor effect, right? Okay, let us screen it back, and we'll get back. We come full circle right now because originally the person who did the experiment wondered if you have a magnetic field and you provide current, it moves, right? And what if you move it? Will we have current or not? That's the whole idea of the Faraday's law. And as you move it, we now know there's current because EMF inducer and everything, right? So the question is, which way is the current? Let's say this is now not the force exerted. This is now the this is not the force exerted. So this F is the exerted force. And আমাকে বের করতে হবে কারেন্টটা কোন দিকে flow করবে in my wire because of this force exerted. Because Faraday's law states what? That if you cut the magnetic field lines, what will be induced? EMF, right? And as EMF is induced, and let's say it's a complete circuit, right? What will start to flow through this? Current, right? Which is the current going to flow? Is it going to be, let's call it A and B, okay? Is it going to be the same as before, A to B, or will it be different? B2? Why? No, but why the right-hand rule? Because the thing is, আমার যদি হচ্ছে FBI, if I'm applying force, if I'm applying current in one way and magnetic flux is the other way, and I get a force, তাহলে এই force এই magnetic flux দিলে তো এই current আসবে কথা. Why do we go there? Because that's what we do, right? We have the right-hand rule. Why? Third law. Lenz's law. Overall Lenz's law. Negative sign. No, that's like because of this. This is the cause. That's the effect. You're telling me the effect. I'm asking you what's the cause. To conserve energy, what's the motion? How does that help? I'd say, okay, did you understand the question? Because I'll give you the answer. The answer is actually straightforward. The question is that in motor effect, if your current goes from here to there, মানে তোমার current হচ্ছে এদিক থেকে এদিকে যাচ্ছে, and this is the magnetic flux, this is the force you experience, right? So if I give this force myself in that same magnetic field, wouldn't I get back the same current? That was the thought process, right? But the current happened to be not the same. The current is actually different. It's B2A, as you guys just claimed, right? So my question is why? So the reason is, it is Lenz's law, but কেন Lenz's law জন্য হয় বলি? So as this coil cuts the magnetic field lines, right? What is induced in this coil? EMF. And because of that EMF, what flows through this coil? A current, right? And the current has to produce a magnetic field toward the motion, oppose the motion. So when you try to take it this way, the current that's generated in this coil is trying to take the wire which way? The other way. So turns out we were doing something wrong entirely from the beginning. The force is not the red arrow. The force is actually the what arrow? The green arrow. This is actually the force that the wire experiences. There are two differences here. What is the force you exert and what is the force that the wire experiences? This is the one, Cano. Because as you try to move this way, according to Lenz's law, this rod wants to stay here. If the rod has to stay here, which way does the rod need to apply force onto itself to stay here? The other way. And that's actually the force that the wire is experiencing. And naturally, the current force if I want to generate that force, which way should the current move? The other way. So it turns out, Fleming's right-hand rule rule because this is still going to work with which rule? Fleming's left-hand rule. Because if you now apply Fleming's left-hand rule with the green arrow, right? The left-hand answer আসে. The problem is that আমরা সবসময় হচ্ছে বের করার চেষ্টা করি using the force we generated. But the wire is not actually experiencing that force. The wire is trying to generate a force to what that force? Oppose it. So which way is the wire actually like creating the force? The other way. And the other way, আমরা answer ভুলে যায়. Now, to accommodate this idea into a way that students don't need to understand this, O levels generate করা হতো the Fleming's right-hand rule. যে যা answer আসবে উল্টা হচ্ছে. But answer কিন্তু সোজাই হচ্ছে. Is that we were taking the wrong force for our assumption. We were using with this force, right? So তোমরা যদি হচ্ছে so the Fleming's left-hand rule is still true here. But there's nothing wrong in the left-hand rule. We just have to take the what force for the left-hand rule to work, the right force. যেটা উল্টা দিকে act করে. Now, if you want to get out of this complexity, there's a simple way out there. Whenever you have a dynamo effect, এটাকে dynamo বলা হয়, or the generator effect, we do the opposite. What do? We use the Fleming's right-hand rule. Our motor effect আমরা কি use করি? The left-hand rule. Okay, so there was a checklist that I showed the other day. Sure. So the dynamo effect is where you are providing force, you're providing flux. What are you looking for? Direction of current. And motor effect, you're providing current, you're providing flux. What are you looking for? Force. So যখন এই dynamo effect আসবে, what do we use? The Fleming's right hand rule. Okay. আর যখন motor effect আসবে, we'll use the Fleming's left hand rule. But essentially, this is actually still using which rule? The left-hand rule. You're just inverting the value. Okay. So yeah, this is Lenz's law and the implication of it. So like a 4-mark question, I should demonstrate Lenz's law. This is the answer. Okay. You basically write about this experiment. Clear about that? So yeah, that's Lenz's law. Question a chapter main impact in the examples I give you. Okay, so this is just the background work. The examples are quite interesting, not challenging, interesting. So এটা কি clear তোমাদের? আমাকে কোনো question থাকলে বলতে পারো. This is basically Lenz's law. Okay, so Lenz's law states that whenever you try to do something, the system will oppose it. Once you see examples, you'll see it makes more sense. And এটা তো just trivial. যে যেতে গেলে oppose করে, বের হইতে গেলে oppose করে. But how does that imply in real life scenario is what we need to look into. Horseshoe magnetটা কেমনে প্লেস করবে বলো? এইভাবে like that. প্রবলেম নেই, এখানে তো এরকম থাকবে ফিল্ড লাইনস গুলো। সো তোমাকে কাট করতে হলে আইদার এইটা বা ওইটার কাছে নিতে হবে, মাঝখান দিয়ে গেলে কাজ করবে না, প্যারালাল হয়ে যাচ্ছে। তো হর্সশু ম্যাগনেটে এরকম ইমাজিন করো নর্থ এন্ড সাউথ, ফিল্ড লাইনস গুলো এভাবে যায় না। সো দিস ফিল্ড লাইনস দ্যাট ইউ সি হিয়ার, দে আর হোয়াট টু দ্য কয়েল parallel, so EMF induced হবে না। So you either have to use the north or the south, একসাথে হবে না। Now you can do it like this though, এখানে নর্থ এখানে সাউথ, এই যে এইভাবে, আর এটাকে যদি মুভ করো তাহলে এখানে EMF induced হবে, and the answer 0 আসবে। So we'll see why, because to me south or north একসাথে কাটতেছে না, cancel out, right? This one up and down, it still doesn't produce field because the field lines go like this, right? These parts are parallel to the coil. Okay, you have to go in and out. That's the best way. Small horseshoe and a large coil. It still cancels out. If you use a very large horseshoe and a small coil, there might not be canceling because you might be at one side or the other side, not both at once. Okay. Okay, so I'll start the examples. It could be important. Okay, the examples I'm going to go through. So at category Korea. There are 7 different examples of increase in difficulty. So Ogla category program. Start with 7.